Let's put the pieces together that we've covered in the last couple of videos and draw a curve of actual rainfall and actual infiltration and infiltration capacity through time, and look at this in a little bit more detail. So, similar axes as before, we will have time on the x-axis. And over here on the y-axis, we're going to have some shared variables. So this y-axis, I'm going to draw multiple things on it. One of those is going to be the infiltration capacity. That'll be our orangish color here. And I'm also going to draw on the same axis another variable, which I'll call I of t. And I of t is going to be the rainfall intensity. Both of these have dimensions of length per time, so centimeters per hour, for example. So let's first draw our infiltration capacity. It's the same deal as before. It starts at some rate f naught, and it goes to some rate, some equilibrium value f sub c, in some decreasing exponential fashion. Okay, let's now draw our our rainfall intensity. So here, maybe the first hour, it's something like this. It goes up like this. It starts to go even higher. So this is the storm that's happening. Then it goes back down. A plot of rainfall intensity versus time has a special name. It's from the Greek, hydrograph. So if I were to draw something like the actual infiltration rate, well, I know that this stuff, the rainfall intensity is lower than the infiltration capacity. The ground has no problem soaking this water up. So it's all going in here. But right here, something's going to happen. It's going to be raining harder than the capacity of the ground to soak up that water. So the actual infiltration rate is just going to be the area under this curve. And we need to talk about what happens to the area above the curve. Actual infiltration rate. Above the curve, in the beginning, remember with our little drawing, we saw once the ground can no longer soak up the water, it starts to pond. And so there's a little bit of time, I'll denote it with these dots, in here, maybe it just lasts this long, where the water goes into depression storage. And the volume of that water is going to be, well, this rate minus this rate times the length of time. This particular point here has a special symbol, T sub P, the time of ponding, or when the rainfall intensity first exceeds the capacity of the ground to soak that up. The rest of this water is going to have yet another fate. It's still raining. All of the depressions on the ground surface have been stored. The ground can't soak up any water any faster. In fact, the rate's still decreasing. And so this zone here on the plot is going to be going to overland flow. In particular, this is a kind of infiltration excess overland flow. Some people call it Hortonian overland flow after Horton. But in general, we'll summarize what we've learned here with this little exercise by saying whenever the precipitation intensity exceeds the infiltration capacity, the infiltration capacity, ponding, and then overland flow